Okay. Hey everyone. Welcome to the last talk of robust speech recognition challenge at Hugging Face. The last talk will be given by Changhan Wang, who is a research engineer at Meta AI working on speech. And the talk is about XLSR, which is a large scale model for cross-lingual speech representations, and which is this is the model that you will be using this for the sprint. So, without any delay, I'll hand it over to you, Shangan.
Cool. Thanks, Raj, for the introduction, and also thanks, Hugging Face, for having me here. So yeah, hi everyone. I'm Changhan. I'm research engineer from Meta AI, mainly working on speech translation and speech representation learning. So today I'm going to talk about XLSR, our recent work on large-scale speech representation learning on as many as 128 languages. So this is a joint work with my colleagues at Meta AI and also Patrick here at Hugging Face. So overall, XLSR is a Wave2Vec 2.0 model. So let me first give you a quick introduction on Wave2Vec 2.0. Basically, Wave2Vec 2.0 is a self-supervised model for learning speech representations. So this learning process requires only unlabeled speech audio data, which is much easier and cheaper to get compared to labeled data. And it provides pre-trained models for many downstream speech tasks, like speech recognition, speech translation, speaker identification, language identification, and so on. So this unsupervised pre-training approach is very helpful to reduce the need of label data in the downstream tasks. Many you may need only a small amount of label data during model fine-tuning to achieve good results on the downstream tasks. For example, we evaluate on the speech recognition task using the Libre Speech benchmark. We show that Wave2Vec 2.0 can beat the previous state-of-the-art with 100 times less labeled data. So the previous state-of-the-art leveraged around 100 hours of labeled data, while in contrast, the Wave2Vec 2.0 model outperforms it with only 1 hour of labeled data. This technique can save a lot of efforts and cost on data labeling. Moreover, when we use the same amount of label data as that was used in the previous state-of-the-art, Wave2Vec 2.0 model can perform even better with a larger improvement of 3.6 decrease on the wear rate in the Libre Speech benchmark. So going back to XLSR, XLSR is a multilingual Wave2Vec 2.0 model. So it's a single model that is trained jointly on 128 languages and supports 128 languages in this one single model. We use a large amount of unlabeled speech audio data to train this model, and we scaled the model size up to 2 billion parameters. So in this way, we are able to make the model generalize well across different languages and domains. We verified the effectiveness of this model on various downstream tasks like speech recognition, speech translation, and speech classification. But however, please note that like XLSR is not limited to these tasks mentioned above. We hope to work with the community to apply and validate XLSR on more speech tasks. And here is a comparison between XLSR and XLSR 53, which is the previous largest multilingual Wave2Vec 2.0 model. We can see that the data scale and model scale have increased significantly from XLSR 53 to XLSR. For example, we scaled the number of languages by 2.4 times, reaching 128 languages. And we scaled the amount of data by almost 8 times, reaching 436,000 hours. And we used data from 5 different datasets / domains compared to 3 datasets in the XLSR 53 model training. We scaled the model size by almost 7 times, reaching around 2 billion model parameters. We'll see later in the downstream task evaluation that these scaling efforts result in huge performance improvements. So for experimentation and different application scenarios, we trained XLSR in 3 different model sizes. The 0.3 billion model to match the size of XLSR 53, the previous state of the art. And we also have the 1 billion and 2 billion models for more model capacity to push the performance limits. XLSR covers 128 languages, but these languages by nature do not have equal number of speakers in the world and equal amount of open data for model training. We can see from the figure on the bottom right that the data distribution by language is very long-tailed. There are only 24 high-resource languages with more than 1,000 hours of training data. And there are 87 low-resource languages which have less than 100 hours of training data. One of the advantages of multilingual models is that joint training on many languages enables cross-lingual knowledge transfer from high-resource languages to low-resource languages. That is, learning on the low-resource languages can benefit from the learning on their related high-resource languages. This brings performance improvements to the low-resource languages without using any more data in those low-resource languages. And this is very good news because for low-resource languages, data acquisition is usually difficult and costly. While for high-resource languages, data acquisition is relatively easier. Next, let me show you some evaluation results on the downstream tasks. So the first one is the challenging speech recognition benchmark, BABEL. So we pick 5 languages from the BABEL corpus and use the average word error rate for evaluation. The BABEL corpus consists of phone call recordings, which have heavy background noises. And the data is low resource with only 30 to 76 hours of data per language. In this setting, XLSR 0.3 billion model outperforms the previous state-of-the-art XLSR 53 with the same model size. There's a significant improvement of 1.4 on the word error rate, and this is because we trained the XLSR model on much more data. The 5 languages are not only covered by in-domain pre-training data from BABEL, but also covered by out-of-domain pre-training data like VoxLingua 107 corpus. The latter provides additional useful information from the same language, and this leads to the performance improvement. We also see a clear trend that increasing the model capacity unlocks more gains. For the larger 1 billion and 2 billion XLSR model, we see that the decrease on the word error rate is enlarged from 1.4 to 3.9 and 4.7 respectively. Here's another challenging speech recognition benchmark, a future setting for 10 languages in the CommonVoice corpus. In this setting, we only have 1 hour of labeled training data for each language, and they are crowdsourced from diverse speakers in the CommonVoice community. Again, we see that XLSR 0.3 billion model significantly outperforms XLSR 53, the previous state of the art. We noticed that the performance can be improved a lot by scaling only the unlabeled data in the same language while using the same small amount of labeled data. So this is a more economic way than increasing the labeled data. An example for this is Swedish. So if you look at Swedish, where like XLSR has 16,000 hours more unlabeled data than the XLSR 53. So this brings a large decrease of 6.7 on the phoning error rate, while it still use the same amount of 1 hour labeled data. Another observation is that out of language data is helpful. For example, on Kyrgyz, XLSR and XLSR 53 have the same training data from CommonVoice, but XLSR contains more data for the other languages. The increased amount of data in the other languages, especially those similar languages from the same language family as Kyrgyz, helps the performance on Kyrgyz through cross-lingual knowledge transfer. Lastly, we again see the trend that like increasing XLSR model capacity enlarges again. In this case, from 1.1 phone error rate decrease to 2.7 phone error rate decrease in the 2BM model. Besides speech recognition, we also evaluate our models on multilingual speech-to-text translation. The task is to build multilingual translation models to translate speech in any of the 21 languages into English. In this task, XLSR 1 billion and 2 billion models achieve large improvements on the mid-resource and high-resource directions. On the 5 mid-resource directions, XLSR 2 billion model improves the state of the art by an average of 7.5 BLEU points. And on the 12 low resource directions, it improves the state of the art by an average of 9.2 BLEU points. So similar to the case in speech recognition, we find that large XLSR models can do much better future learning. For example, on the Swedish to English direction, where there's only 2 hours of label data, XLSR 2 billion model outperforms the previous state of the art by as many as 19.3 BLEU points. And similarly on the Arabic to English direction, where we also have only 2 hours of label data, there's a substantial improvement of 14.1 BLEU points. Comparing the performance for XLSR 0.3 billion, 1 billion, and 2 billion models, we again confirm the trend that more model capacity in XLSR brings more gains. Here's another similar multilingual speech-to-text translation task where we want to build multilingual models to translate English speech into any of the 15 target languages. We also see, we already see from the previous experiments that like XLSR brings large gains to mid-resource and low-resource directions. In this experiment, we instead focus on the high-resource side and take English as example because in general, it's the highest resource language in speech research. In this setting, we compare XLSR models with English only wave-to-vector models And we see that like our large 1 billion and 2 billion models outperform these strong Multilingual baselines. And this confirms that XLSR performs well across languages, regardless of the data condition. And cross-lingual knowledge transfer helps the low-resource languages without hurting much the performance on the high-resource languages. Besides speech recognition and speech translation tasks, we also see the benefit of XLSR models on speech classification tasks. For example, on the language identification task, where we test the identification of 33 languages using the VoxLingua 107 corpus. The XLSR 0.3 BDM model outperforms the previous state-of-the-art by 1% error rate. On another task, the speaker identification task, where we use the VoxLab1 dataset to test the identification of around 1,000 celebrity voices, XLSR 0.3 BDM model outperforms the previous state-of-the-art by 5.5% accuracy. So here is a quick summary for XLSR. Basically, XLSR is our latest multilingual wave-to-vec 2.0 model supporting 128 languages. We provide 3 model sizes, 0.3 billion, 1 billion, 2 billion for different application scenarios. The 0.3 billion model consistently outperforms the previous state-of-the-art multilingual wave-to-vec 2.0 model, namely XLSR 53. And it's a drop-in replacement with identical model architecture and equal model size. The 1 billion and 2 billion models have more model capacity, and these unlock more performance boosts, especially on the mid-resource and low-resource languages. At the same time, these large XLSR models also perform comparably or even better on high-resource languages like English when compared to large monolingual pre-trained models. So overall, it's suggested that large XLSR models are universal models for all the languages. They perform well across high-resource, mid-resource, and low-resource languages, and they may replace many former multilingual or monolingual wave-to-vec 2.0 models for better performance. So next, I just want to share some quick notes for using XLSR models. So basically, we released the pre-trained models, fine-tuned multilingual speech translation models for both foreign to English and English to foreign directions. So these models are in 3 different sizes, 0.3 billion, 1 billion, and 2 billion. You can use the original fair segmentation to run model inference. Just check out the wave2vec and XLSR example folders in the FairSig GitHub repo for the model links and instructions. And it's even more convenient to use the implementation in the Hugging Face Transformers library. We also provide an example for this in the FairSig repo. To fine-tune XLSR models or a new language or a new data set by yourself using Hugging Face Transformers library, Patrick actually wrote a really nice tutorial and provided great detailed examples in this tutorial. And I strongly recommend you to check it out. And if you'd like to try also the FairSig implementation, feel free to check out our note in the XLSR example folder in the FairSig repo. All right, so that's all for my presentation. Thanks for your attention, and I'm happy to answer questions now.
Thanks a lot, Changhan, for the great talk. And we have quite a few questions. I'll just read it out to you. So
Sure.
Steven is asking, I'm curious about the upscaling approach. Do you have any results or insights from different values of alpha? And how about for monolingual batches instead of multilingual sampling language per batch?
Sure, this is a good question. Yeah, so I think upsampling is kind of um, a question for many multilingual models, especially for multilingual models involves a lot of languages. So for our case, we use temper-based. We just follow the previous best practices. So we just use temper-based upsampling with the temperature of 2. So we did try with different temperatures in this upsampling and find this one is generally provides the best performance. So for the second question, for batching, um, yeah, so I think currently we didn't actually uh, like deliberately match like mixing the data from different languages in one batch. So the current batching strategy, like we still target at better efficiency during training. So we kind of saw the languages, saw the examples by their length, and like it's possible like in some of the batches is purely monolingual because it's decided by the length.
Cool. The next question is by Patrick. For speech translation, the language model was integrated within the architecture, and whereas for ASR, language model boosted decoding is used mostly. So, would it make sense to use the seek-to-seek architecture for ASR as well?
Yeah, I think that's a good question. I think um, yeah, definitely. I think for ASR, LM decoding can be very useful, especially for the low resource uh, settings where we don't really have much label data, and LM decoding can provide additional information on the target language. I mean, for ASR, it's just in the same language, but it provide additional linguistic information to improve the decoding results. And at least I think for fear's sake, we do have the implementation for LM decoding for the general Bing search decoding. So that covers both speech translation and ASR. So
The next question is also by Patrick. Do you think a minimum amount of capacity is required? For example, could one pre-train a 100 million parameter model on 128 languages? Or is this too much data for too little parameters?
yeah, this is a good question. So we built 2BM model, like we use a lot of model capacity because like for these 128 languages, they there may be very distinct languages, like from different language families, right? And for multilingual models, there are interference issues because like you may see like two very different languages, they are competing for the model capacity. So that's why we want to use large model capacity to ensure that like we can minimize this interference and the model can perform well on all the languages. So back to the questions of small multilingual models, one one suggestion is that like maybe we can try to, I think a trade-off for this, like instead of training a small model on all the 128 languages, maybe you can try to train it um, on the languages from the same language family, and hopefully like there are smaller interference issues on these languages from the same language family, and hopefully like the small multilingual models can perform well on this.
Cool. The next question is about whether using groups of language families in pre-training would provide better performance than grouping unrelated languages together.
Yeah, so yeah, I think this kind of relates to what I said just now. So yeah, I think um yeah, so I think overall like our initial goal is like trying to build a universal model. So just trying to combine all the possible data and support as many languages as possible in XLSR. but as I mentioned, like sometimes we need to want to make trade-off. Like say when you really have a limit on the model size, want to pursue smaller model size, and in this case, maybe you want to trade this like trade the number of supported languages for like better performance on smaller data. So in this case, I would say like training multilingual models on the same language family will make more sense. Um, yeah, so I'm not really sure about this two-step pre-training mentioned here. I guess maybe does that mean like say you just pre-train the model first by language family and then by all the languages? Yeah, I'm not super sure about the detail. It'd be great if you can provide some clarification.
Okay, we'll take two last questions. So it's about like, have you tried or will you try to scale up even further?
Yeah, the answer is yes. So we are working on this. So we've seen like in the slides that like on speech recognition and speech translation. So there's a clear trend of LSR XLSR model getting better performance by scaling up, right? So it's not even like saturating yet. So currently we are working on even larger models to see if we can push the limits further.
Awesome. Thanks a lot, Changhan. We have also reached our time limit. Thanks a lot for the wonderful talk. And thank you, all of you, for joining us. We are very excited to see what you are going to build in this challenge. Have a good evening, or a good day. And thank you.
All right, thank you very much. Have a good one, everybody.
Bye, everybody.